In the unending silent blackness of the cosmos, humanity has always posed a single, haunting question. Are we alone? For millennia, we have gazed up at the tapestry of night, a glittering vault of countless stars, and wondered if, on some distant shore of that cosmic ocean, another consciousness looks back. Our search for an answer has been a story of ever-sharpening vision, from the naked eye to the first crude lenses of Galileo, each step a leap forward into the grand unfolding mystery. But the universe has held its secrets close, offering only a profound and echoing quiet. We have found gas giants and frozen wastelands, worlds of fire and spheres of diamond rain, yet a true echo of our own world, a planet that could harbour the familiar chemistry of life, has remained elusive. Perhaps we were looking in the wrong places. Perhaps we were too focused on finding a mirror of ourselves, a twin to our own sunlit home. Now a new eye has opened onto the universe. An eye of unprecedented power, forged from gold and beryllium, cooled to the very edge of absolute zero. It is an instrument so sensitive it could detect the heat signature of a bumblebee on the surface of the moon. This revolutionary sentinel, the James Webb Space Telescope, has begun to peel back the veil, and in the faint ancient light from a star system 40 light-years away, it has confirmed something extraordinary. It has focused its gaze on a small, dim star, a type of celestial furnace so common it outnumbers all others, and found a world nestled perfectly in its gentle warmth, a planet named TOI 700D. This is the story of that world, of the technological marvel that revealed it, and of how this single discovery may force us to rewrite our understanding of life in the universe. It is a tale that begins not in the cold of space, but in the fire of human ambition. The quest to build the James Webb Space Telescope was a journey of decades, a testament to human ingenuity and persistence. It was conceived as the successor to Hubble, a machine that had already transformed our cosmic perspective. But Webb was designed to see what Hubble could not, the very dawn of time. To do this, it needed to capture the faintest, most ancient light in the cosmos, light that has been travelling for over 13 billion years. As this primordial luminescence journeys across the expanding fabric of space-time, its wavelength is stretched, shifting from visible light into the infrared spectrum. Our eyes cannot perceive this ghostly glow. Hubble could only glimpse it. Webb was designed to live in this realm of cosmic ghosts. Its heart is a mirror of breathtaking scale and precision. 18 hexagonal segments of ultralight beryllium, each polished to a smoothness measured in atoms, then coated in a microscopically thin layer of pure gold. Gold is exceptionally reflective of infrared light, making it the perfect surface to gather these whispers from the past. Unfurled in space, these segments form a single, immense honeycomb structure over 6.5 meters across, a golden flower opening to the cosmos. Building such a mirror was an engineering challenge of Herculean proportions. It had to be strong enough to survive the violent vibrations of a rocket launch, yet light enough to be lifted from Earth's gravitational grasp. Most critically, it had to be folded, like a piece of cosmic origami, to fit inside the nose cone of its launch vehicle. The mechanism to unfold and align these 18 segments in the frigid vacuum of space, with each mirror positioned to an accuracy smaller than a human virus, represents one of the most complex deployments ever attempted. But this magnificent golden eye could not function without its guardian. To see the faint infrared heat of distant galaxies, the telescope itself must be phenomenally cold. Any heat from the observatory would blind its sensitive instruments, washing out the ancient signals it seeks. It needed a shield, a parasol of epic proportions to block the light and heat from our own sun, Earth and Moon. The solution was a 5-layer sun shield the size of a tennis court. Each layer is made of a material called capton, thinner than a human hair and coated in aluminum and silicon. These layers are separated by a vacuum, creating an incredibly effective thermal barrier. The sun-facing side of the shield can reach a scorching 85 degrees Celsius, while on the other side, in the perpetual shadow, the telescope's instruments operate at a mind-numbing -233 degrees Celsius. This temperature difference, akin to standing in boiling water, and dipping your hand in liquid nitrogen at the same time is maintained across just a few feet of space. To achieve this isolation, Webb could not orbit the Earth like Hubble. It had to journey to a unique point in space, 1 million miles from home, a place called the Second Lagrange Point, or L2. Here, the gravitational pull of the Sun and Earth balance perfectly, allowing the telescope to remain in a fixed position relative to us, keeping its sun shield permanently positioned to block all sources of terrestrial heat. The journey to L2 was a month-long nail-biting odyssey. After its launch on Christmas Day 2021, the world watched as hundreds of deployment steps had to execute flawlessly. The unfolding of the sun shield, the tensioning of its membranes, the locking of the mirror wings into place. Any single failure would have doomed the $10 billion mission. But each step succeeded. The golden eye opened, and humanity gained a new window into the deepest, darkest, and oldest corners of creation. While one of its primary missions is to look back to the cosmic dawn, Webb is also a revolutionary tool for exploring the worlds orbiting other stars. It is an exoplanet hunting machine of unparalleled power, and it was this capability that was brought to bear on a faint point of light in the constellation Dorado. The story of TOI 700D, however, does not begin with Webb. It begins with another vigilant satellite, a planet hunter named TESS, the Transiting Exoplanet Survey Satellite. Launched in 2018, TESS's mission is to conduct a sweeping survey of the entire sky, observing hundreds of thousands of the brightest and nearest stars, searching for a telltale sign of a hidden world, a transit. Imagine sitting miles away from a powerful distant lighthouse. The beam is steady, a constant source of illumination. But then, for a brief fleeting moment, a tiny moth flies directly in front of the bulb. From your vantage point, you would see a minuscule, almost imperceptible dip in the lighthouse's brightness. If you saw this dip repeat at regular intervals, you could deduce the moth is circling the light. You could even learn about its size from how much light it blocks, and its orbital period from the timing of the dips. This is the transit method in its essence. TESS stares, unblinking, at star after star, measuring their brightness with exquisite precision, waiting for the shadow of an orbiting world to pass across the face of its stellar parent. In 2020, TESS was observing a small, cool star designated TOI 700, which stands for TESS Object of Interest. This celestial body is not like our Sun. It is a red dwarf. These are the most common types of stars in our Milky Way galaxy, making up roughly 75% of the stellar population. They are small, faint, and ancient, sipping their hydrogen fuel so slowly they can live for trillions of years, far longer than the projected 10 billion year lifespan of a sun-like star. As TESS monitored this placid red dwarf, it detected not one, but a series of rhythmic dips in the starlight. The data pointed to a system of at least 3 planets. The innermost world, TOI 700b, was a rocky, Earth-sized planet, but orbiting so close to its star that its surface would be a furnace. The next planet out, TOI 700c, was a larger gaseous world, a mini Neptune, also outside the realm of habitability. But the third signal, the faintest of all, was the most tantalizing. It suggested a planet just about the size of Earth, orbiting its star every 37 days. Calculations showed that this orbit placed the world, now named TOI 700d, squarely within its star's habitable zone. The habitable zone, often called the Goldilocks zone, is the orbital region around a star where conditions are not too hot and not too cold, but just right for liquid water to potentially exist on a planet's surface. Water is the one ingredient we know to be essential for life as we understand it. Too close to the star and water would boil away into space. Too far and it would freeze into a permanent global ice age. TOI 700d appeared to be in that perfect temperate lane. The discovery was electrifying, an Earth-sized planet in the habitable zone of a nearby star. But TESS's data, while compelling, was just the beginning. The transit method can be fooled by other cosmic phenomena, such as a pair of eclipsing binary stars in the background. Confirmation was needed from other observatories. Ground-based telescopes and NASA's Spitzer Space Telescope were brought in, and they confirmed the existence of the planet. The moth was real, A world was truly there. But this confirmation only deepened the mystery. Was it just a barren rock, or did it possess an atmosphere? And if it had an atmosphere, what was it made of? These were questions that pushed beyond the limits of existing technology. Answering them required a new level of observational power. It required an instrument that could not just see the shadow of the world, but could analyse the starlight that filtered through its air. Answering them required the golden eye of Webb. When Webb turned its attention to the TOI 700 system, it wasn't just to reconfirm the planet's existence. Its mission was far more profound: to begin the search for an atmosphere. The technique it employs is called transmission spectroscopy, a method of extraordinary subtlety. Let's return to our lighthouse analogy. Imagine now that the moth flying in front of the light has wings made of coloured glass, perhaps a mix of red and blue panes. When the moth passes in front of the lighthouse beam, the pure white light shines through its wings. The red glass will absorb all the other colours and let only red light pass through. The blue glass will only let blue light pass. If you had a special camera that could analyse the spectrum of the lighthouse beam, you would notice that when the moth is in transit, specific colours from the white light are suddenly missing, absorbed by its glassy wings. By identifying which colours are absent, you can determine the composition of the glass. This is precisely what Webb does. When TOI 700D passes in front of its star, a tiny fraction of the starlight filters through the planet's atmosphere, if one exists. Molecules in that atmosphere, water vapour, methane, carbon dioxide, each absorb very specific wavelengths, or colours, of infrared light. They leave a unique chemical fingerprint, an absorption signature, embedded in the starlight. Webb's powerful spectrographs, like the near-infrared spectrograph or NIR spec, are those special cameras. They can capture the starlight, spread it out into a rainbow-like spectrum of thousands of individual shades, and measure the precise brightness of each one. By comparing the spectrum of the star when the planet is in transit to when it is not, astronomers can pinpoint exactly which wavelengths have been absorbed by the atmosphere. They can read the barcode of an alien sky from 40 light-years away. The observations of TOI 700D were among the very first of their kind for Webb, a crucial test of its capabilities. The data streamed back across 1 million miles of space to Earth, a collection of photons that began their journey before many of us were born. Scientists around the world held their breath. The results were a stunning success. Webb not only confirmed the planet with irrefutable clarity, but its measurements were so precise that it refined our knowledge of the world. It is now known to be 95% the size of Earth, almost certainly a rocky terrestrial planet. The initial observations have not yet definitively confirmed the presence of an atmosphere, let alone its composition. That process is painstakingly slow, requiring many more transits to be observed to build up a strong enough signal. The hint of an atmosphere is tantalizingly there, but the data is not yet conclusive. However, what Webb's confirmation has done is elevate TOI 700D from a curious candidate to a prime target. It has proven that this world is one of the most compelling places we have ever found to search for the signatures of life. It is a stable, Earth-sized world in a temperate orbit. But the nature of its sun, the red dwarf TOI 700, makes this prospect both fascinating and fraught with peril. Life on a planet orbiting a red dwarf would be utterly alien to our own experience. To imagine standing on the surface of TOI 700D is to picture a scene from a science fiction novel. The sky would not be a familiar blue. Red dwarf stars emit most of their energy in the red and infrared parts of the spectrum. The heavens above would likely be cast in a perpetual dusky twilight, a palette of deep oranges and bloody crimsons. The sun itself, the red dwarf TOI 700, would appear larger in the sky than our own sun, because the planet must orbit much closer to its cooler star to stay within the habitable zone. This proximity creates a profound and bizarre environmental condition: tidal locking. Just as the Earth's gravity has locked one face of our moon to permanently point towards us, the red dwarf's intense gravity would likely lock TOI 700D. One hemisphere of the planet would be trapped in eternal daylight, its landscape baked under a relentless, unmoving crimson sun. The other hemisphere would be frozen in endless night, a realm of profound cold and darkness. Life, if it were to exist, would be unlikely to thrive in these extremes of fire and ice. But between these two desolate zones, there would be a sliver of hope. A twilight region, a terminator zone, where the sun hangs forever on the horizon, neither rising nor setting. In this band of eternal dawn or dusk, temperatures could be moderate enough for liquid water to flow. Winds of unimaginable force might rage across the planet as the atmosphere from the hot side rushes towards the cold side, creating a global weather pattern unlike anything on Earth. Perhaps in this twilight ring, life could find a foothold. If plant-like organisms were to evolve here, they would face a different challenge. Photosynthesis on Earth is optimized for the yellow-white light of our sun. To capture the energy from a dim red star, alien plants might evolve different pigments. Instead of the vibrant greens of Earth's forests, the flora of TOI 700D might be a shocking deep purple, or even black, to absorb as much of the available light energy as possible. A journey through a forest on this world would be a surreal experience, through groves of dark, brooding vegetation under a sky the colour of wine. But there is a more violent threat that looms over any potential life in a red dwarf system. These stars, particularly in their youth, are notoriously tempestuous. They can unleash stellar flares of incredible power, far more energetic than those from our own sun. These outbursts of high-energy radiation and charged particles could be catastrophic for a nearby planet. A single superflare could strip away a planet's atmosphere over time, boil off its oceans and douse its surface in sterilizing radiation. For life to survive, TOI 700D would need powerful defenses. A strong planetary magnetic field could act as a shield, deflecting the worst of the stellar wind. Or perhaps life would have to evolve entirely underwater, with the oceans providing a protective blanket against the fury of the sky. TOI 700, fortunately, appears to be an unusually quiet and stable red dwarf, showing no evidence of these violent flares in the time it has been observed. This placid nature significantly boosts the chances for its planetary companion. And while the challenges are daunting, the greatest gift a red dwarf offers to the prospect of life is the one thing it has in abundance: time. Our sun is in its middle age, with about 5 billion years left before it swells into a red giant and consumes the inner planets. Life on Earth had a limited window of opportunity to arise and evolve intelligence. Red dwarfs, however, will burn for trillions of years. They are the last lights of the universe, the embers that will glow long after every sun-like star has faded. This almost incomprehensible lifespan provides a cosmic crucible of immense duration. On a world like TOI 700D, life would not need to be rushed. It would have billions, even trillions of years to emerge from the primordial soup, to evolve, to diversify, and perhaps to achieve consciousness. When our own solar system is nothing but a cold memory, life on the worlds of red dwarfs could just be hitting its stride. This discovery, therefore, does more than just add another pin to our map of exoplanets. It fundamentally shifts our perspective. The confirmation of TOI 700D by the James Webb Space Telescope represents a watershed moment in our search for life. For decades, our quest has been dominated by the search for an Earth 2.0, a rocky planet orbiting a G-type main sequence star, a celestial twin to our own sun. This was a natural conservative starting point. We were looking for what we knew, but the universe may not be so limited in its imagination. Red dwarf systems present a completely different paradigm for habitability. They force us to think beyond blue skies and green forests, to envision life thriving in conditions that would seem utterly alien to us. They suggest that the most common locations for life in the cosmos might be these twilight worlds under crimson suns. If life can indeed take hold in such systems, the implications are staggering. Given that red dwarfs are the overwhelming majority of stars, this would mean the number of potentially habitable worlds in our galaxy is not in the millions, but in the tens of billions. The great silence that has puzzled scientists, the Fermi paradox, which asks, if the universe is full of aliens, where are they? Could have a simple answer. We were listening on the wrong frequency, looking at the wrong kind of star. Perhaps the galactic conversation is happening in the dim, red light we have only just begun to scrutinize. The journey with TOI 700D is far from over. This is merely the first chapter. Webb will return its gaze to this distant world again and again, staring for hours during each transit, slowly building the data needed to solve the riddle of its atmosphere. Each observation will add another piece to the puzzle. Will we find the telltale absorption lines of water vapour, hinting at oceans and clouds? Will we detect methane or carbon dioxide, suggesting geological or even biological activity? The ultimate prize, of course, would be the detection of biosignatures, gases like oxygen or ozone, which on Earth are overwhelmingly produced by life itself. Finding such a signal in the air of TOI 700D would be a discovery that would change human history forever. It would be the moment we could finally say with scientific certainty that we are not alone. But even if TOI 700D turns out to be a sterile rock, the path it has illuminated remains. Webb is now examining other promising red dwarf systems, like the famous TRAPPIST-1 system, which hosts at least 7 Earth-sized planets, several of which are also in the habitable zone. Each observation is a roll of the cosmic dice, a new chance to find the evidence we seek. This telescope is more than just a machine of glass and gold and wire. It is the physical embodiment of our deepest, most primal curiosity. It is the sharpened spearhead of our species' quest to understand our place in the universe. From the first hominid who looked at the moon and wondered, to the engineers who meticulously folded a golden mirror, the same spirit of inquiry drives us forward. We look out into the cosmic darkness, not with fear, but with a relentless and hopeful sense of wonder. TOI 700D is a potent symbol of that hope. A small, rocky world, orbiting a quiet, long-lived star, offering a tantalizing hint that the ingredients for life are not a cosmic fluke, but a common feature of the universe's grand design. We do not yet know what mysteries lie on its surface, beneath its crimson sky. We do not know if anything stirs in its potential oceans, or if any strange dark forests reach for the light of their undying sun. For now, it remains a point of light, a whisper of a possibility. But for the first time, we have an instrument powerful enough to listen to that whisper, to decode its meaning, and perhaps to finally hear an answer to that ancient, persistent question that has echoed through all of human history. Is anybody out there? The universe has been silent for a long time, but now we are truly beginning to listen. There is a place in the universe where the rules of creation are not just broken but inverted. It begins in an abyss, a wound in the fabric of space-time itself, where a monster of impossible gravity lies in wait. This is the domain of the supermassive black hole, a gravitational monarch holding court at the heart of a galaxy, its silent, suffocating presence dictating the fate of 100 billion stars. You've been taught to think of these objects as cosmic endings, as the universe's ultimate dead ends where light matter and time itself surrender. And for the most part, you would be right. To approach one is to witness a spectacle of celestial violence that dwarfs any other force in the cosmos. Matter drawn from the surrounding galaxy like water swirling toward a drain does not fall in quietly. It forms a sprawling, luminous nightmare known as an accretion disk. Here entire solar systems are shredded into their constituent atoms, a cosmic traffic jam of gas and dust and the ghosts of devoured stars all spiralling toward a point of no return. The friction within this celestial mosh pit is so immense, the sheer pressure so mind-breakingly powerful, that the disk ignites into a blaze of light brighter than the entire host galaxy combined. It becomes a quasar, the most luminous object we can see a lighthouse, burning at the edge of the observable universe, fueled by the death throes of everything that wanders too close. This is not a place for life. It is not a place for beginnings. The radiation blasting from this disk is a sterilizing wave, capable of scouring the atmospheres from planets light years away. The temperatures are measured in millions of degrees, a searing furnace where the very concept of a stable molecule is a fantasy. This is an environment of pure, unadulterated chaos, an engine of annihilation powered by the fundamental force of gravity. It is by every law of physics we hold dear the most hostile, most destructive, most infertile location in all of creation. And yet, it is from the very heart of this maelstrom, from the precipice of oblivion itself, that something impossible emerges. Out of the churning core of the accretion disk, channeled by magnetic fields, twisted into unimaginable strengths, the black hole unleashes its fury. It ejects twin jets of plasma, two colossal pillars of energy, and matter blasting away from its poles at nearly the speed of light. These are not mere plumes of gas, they are relativistic particle cannons. Each jet is a focused, coherent beam of subatomic particles, superheated to a state that has no earthly equivalent. They act as cosmic blowtorches slicing through the galaxy for thousands, sometimes millions of light years. When one of these jets strikes a cloud of interstellar gas, the collision is an event of staggering ferocity. The shock wave alone is enough to vaporize entire star systems. The turbulence it creates is supersonic, a tempest that should tear any structure apart. This is the ultimate paradox, the central confounding mystery that brings us here. Because it is inside this pillar of destruction, within this torrent of energy designed to shred and obliterate, that we are now witnessing an act of cosmic rebellion. We are seeing stars being born, not near the jet, not in the aftermath of its passage, but inside it. Tiny, brilliant blue points of light newborn suns igniting within the inferno. It's like watching a candle being lit in the heart of a hurricane, a flower blooming in the throat of a volcano. It simply should not be happening. To understand the sheer absurdity of this discovery, you must first appreciate the delicate, almost sacred conditions that are normally required for a star to form. Starbirth is not a violent act. It is a process of quiet, patient accumulation. It begins in the coldest, darkest, most serene corners of a galaxy, in vast, tranquil clouds of molecular hydrogen and dust. We call them stellar nurseries, and the name is deeply appropriate. These are cosmic cathedrals of silence and shadow places where temperatures plummet to just a few degrees above absolute zero. In this profound cold, the otherwise chaotic motion of gas atoms slows to a crawl. This is the crucial first step. For a star to be born, gravity, the weakest of the four fundamental forces, must conquer the inherent pressure of the gas. It needs time. It needs stillness. It needs the gas to be cold and dense enough for its own meagre self-attraction to gently, painstakingly pull it together. Over millions of years, tiny clumps begin to form gravitational seeds that slowly gather more and more material from their surroundings. They grow denser, warmer, evolving into protostars glowing dimly in the infrared spectrum shrouded in their dusty cocoons. It is a process of nurture, of slow gravitational collapse, a cosmic gestation period that cannot be rushed and must not be disturbed. Any significant disruption, a nearby supernova, a blast of radiation, or a violent shock wave can shatter these delicate stellar embryos. The injection of heat or turbulence would raise the gas pressure, and gravity's fragile hold would be broken. The cloud would simply disperse its potential for new life scattered to the void. The sanctity of the stellar nursery is paramount. Tranquility is the midwife of creation. Now return with us to the black hole's jet. This is no tranquil nursery. It is the antithesis of one. The jet is a place of unimaginable heat, millions of degrees, where gas pressure is not a gentle force to be overcome, but an explosive outward blast that should defy any attempt at compression. The jet is a torrent of supersonic turbulence, a chaotic flow moving at a significant fraction of the speed of light. Any fledgling clump of gas, any potential stellar embryo should be instantly and violently ripped to shreds by the sheer forces alone. The jet is a fire hose of kinetic energy, a relentless stream of particles that imparts momentum so great it should blow any gathering cloud apart like cosmic dandelion fluff in a gale. There is no quiet corner here, no patient gathering of matter. There is only a relentless directed onslaught of pure energy. So how can these two realities possibly coexist? How can the universe's most effective sterilizing agent simultaneously become a cradle of stellar life? For decades, our models of galactic evolution were built on a simple, elegant assumption that supermassive black holes and their jets acted as a cosmic thermostat. When star formation in a galaxy ran rampant, producing too many stars too quickly, the black hole at its centre would feed on the abundant gas. It would then roar to life, launching these powerful jets. The jets would heat and expel the remaining gas from the galaxy, effectively shutting down the star-making factories. They were the great regulators, the agents of negative feedback, ensuring that galaxies did not burn themselves out in a single brilliant flash. They were the bringers of order, but it was the order of quiescence of an imposed sterility. This phenomenon we have now discovered, which astronomers have dubbed positive feedback, turns that entire carefully constructed paradigm on its head. It suggests the monster is not just a regulator, but also a creator, that the very mechanism thought to halt star formation can under certain circumstances trigger it in the most unlikely and hostile of settings. The first hints of this cosmic heresy were subtle, buried in the complex data streams of our most powerful telescopes. Astronomers pointing instruments like the Very Large Telescope in Chile or the Atacama Large Millimeter Array at the vast outflows from distant quasars expected to see only disruption. They were mapping the flow of gas being driven out of galaxies, trying to understand the physics of that great galactic shutdown mechanism. Instead, they found something that made them question their own instruments. Embedded within the spectral data from the outflowing gas, they saw the unmistakable chemical fingerprints of young, massive, intensely hot stars. These were brilliant blue-white giant stars with lifespans of only a few million years, meaning they must have formed right there within the jet. They couldn't have been old stars that were simply swept up in the flow. Their lifetimes were shorter than the journey out of the galaxy's core. They had to be newborns. The initial reaction was disbelief. It was a measurement error, a misinterpretation of the data, an artifact of the software. Team after team went back to their observations, recalibrating, reanalyzing, looking for any other possible explanation. Perhaps these were not stars, but strange compact knots of superheated gas that merely mimicked the signature of starlight. But the evidence continued to mount, coming from different galaxies, observed by different teams using different instruments. The conclusion, however improbable, became inescapable. In the outflow of a galactic core where a supermassive black hole was actively feeding new stars were being forged in the heart of the fire, the observations showed that not only were these stars forming, but they were forming at a prodigious rate, creating pockets of new life that were travelling away from their home galaxy at millions of miles per hour. We were seeing stellar nurseries on the run, conceived in violence, and exiled from their galactic birthplace at birth. This discovery doesn't just add a new chapter to our understanding of star formation. It forces us to rewrite the book entirely. It asks us to consider that the universe is more complex, more resourceful, and far more surprising than our models ever allowed. It presents us with a fundamental, compelling question: how? What physical mechanism could possibly allow gravity to win this impossible fight? How can a jet, a force of explosive expansion, somehow create the conditions for intense localized compression? Is there some hidden process at play, a subtle interaction between the jet's shockwave and the interstellar medium that we have never before conceived? Could the jet's ferocious passage through a dense gas cloud create pressures so extreme that it triggers a new violent mode of collapse, a form of shock-induced starbirth that operates on timescales of centuries, not millennia? Or perhaps the jet itself is not a uniform column of energy, but a more complex structure with turbulent eddies and protected pockets where gas can momentarily find refuge and begin the process of creation. The implications ripple outward, touching upon the deepest questions of cosmic evolution. Could this be a missing piece of the puzzle that explains how galaxies grow and change? These exiled stars born in the outflow will not remain in their parent galaxy. They will travel through the desolate space between galaxies, the intergalactic medium seeding it with heavy elements when they eventually die. Could this process be responsible for enriching the cosmic voids, providing the raw material for future generations of stars in unexpected places? Could it even explain the formation of strange isolated star clusters, found drifting in the lonely darkness far from any galactic home? We are standing at the edge of a new frontier in astrophysics where the lines between creation and destruction have become profoundly blurred. The monster we thought we understood has revealed a new creative face. Its roar of annihilation may also be a cry of birth, Our journey to solve this extraordinary puzzle has just begun. We must now venture into the heart of this cosmic storm. We will explore the leading theories born from complex computer simulations that attempt to replicate these impossible conditions. We will meet the scientists who are dedicating their lives to decoding these faint signals from across the universe. And we will travel through the eyes of our most advanced observatories to the very galaxies where this unbelievable act of creation is happening right now. The challenge is immense, for we are trying to observe a delicate process taking place inside one of the most powerful and luminous phenomena in the cosmos. It is a search for a cosmic whisper hidden inside a celestial scream. And the first clue may lie not in the jet itself, but in the unique nature of the clouds it is destined to collide with. For it takes a special kind of environment to turn a cosmic blowtorch into a stellar forge. There is a paradox at the heart of our cosmos, a contradiction so profound it has shaped the very destiny of galaxies. For in the most crowded, most luminous, most creative places in the universe, the swirling cores of spiral and elliptical giants, we find not a cradle of life, but an engine of absolute annihilation. We find the supermassive black hole. This is not the quiet, stellar mass phantom you might imagine born from the collapse of a single star. No. This is a different class of monster altogether, a gravitational titan millions, even billions of times more massive than our own sun, holding the entire galaxy in its thrall. It is the cosmic anchor around which everything we see orbits a silent, unseen sovereign. But this sovereign is not always silent. When it feeds the universe itself bears witness. Imagine a star or a vast cloud of interstellar gas wandering too close to this precipice of space-time. It doesn't simply fall in. The black hole's immense gravity exerts a differential pull, a cosmic torture rack known as a tidal force. The side of the object closer to the singularity is pulled with ferociously more strength than the far side. This stellar victim is stretched, elongated, and then violently shredded into a river of incandescent plasma. This is the beginning of the feast. This river of doomed matter doesn't plunge directly into the abyss. Instead, it is captured in a spiraling descent, forming one of the most extreme structures in existence, the accretion disk. You're looking at a cosmic maelstrom, a flattened spinning vortex of superheated gas and stellar debris wider than our entire solar system. As this material swirls ever closer to the event horizon, the point of no return it's compressed and accelerated to unimaginable speeds. Friction and gravitational shear within the disk ignite a firestorm of staggering proportions. The matter here doesn't just glow, it blazes with a ferocity that can outshine all 100 billion stars of its host galaxy combined. It becomes a quasar, a quasi-stellar object, the most luminous beacon in the known universe shining from the edge of space-time itself. We see its light from across 13 billion years of cosmic history, a testament to the raw power of gravity converting mass into pure terrifying energy. The temperature within this swirling platter of chaos soars to millions of degrees, unleashing a torrent of high-energy X-rays and ultraviolet radiation that floods the galactic core. Yet this blinding spectacle of consumption is only half the story. As the accretion disk spins with furious velocity, it doesn't just generate light and heat. It becomes a cosmic dynamo of almost unbelievable power. The plasma being composed of charged particles drags magnetic fields along with it. The black hole itself, often spinning at a significant fraction of the speed of light, twists the very fabric of space-time in its wake. This combination, the ferociously spinning disk and the space-time dragging singularity, takes the magnetic field lines and winds them up, twisting them into tightly coiled, tower-like structures that extend perpendicular to the disk away from the black hole's poles. Think of it as winding a colossal magnetic spring, storing an amount of potential energy that defies human comprehension. This is the launch pad. This is the engine room for the universe's most powerful cannons. Not all the material in the accretion disk is fated to cross the event horizon. A small fraction, perhaps 10% of the infalling matter is caught in this magnetic crucible. Before it can be devoured, it is captured by these violently twisted magnetic funnels. It is then redirected, collimated into a narrow-focused stream, and subjected to an acceleration so extreme it feels like a physical impossibility. This plasma is flung outwards away from the black hole, catapulted along these magnetic highways, into intergalactic space. It is launched at speeds that are genuinely astronomical 1995, sometimes more than 99% of the speed of light. This is a jet. But that simple four-letter word is a profound understatement for the reality it describes. This is not a stream of water from a hose. This is a focused, sustained galaxy-spanning blast of elemental particles and radiation, a celestial blowtorch that can extend for hundreds of thousands, sometimes millions of light years. It drills clean through its own galaxy's interstellar medium and pushes out into the vast dark emptiness between the great cosmic cities of stars. From our vantage point on Earth, our radio telescopes see them as ghostly ethereal plumes, magnificent and silent. But this silence is an illusion of distance. If we could hear them, the sound would be a continuous, deafening roar, the thunder of creation's most violent process. For decades, our understanding of these jets was unambiguous, a settled and fearsome truth. They were agents of destruction. They were the enforcers of cosmic sterility, magnificent but utterly hostile to the gentle process of creation. The reasons for this scientific certainty are stark, written in the fundamental laws of physics. First, and most obviously, is the sheer overwhelming heat. The plasma within the jet itself exists at temperatures of millions, sometimes tens of millions of degrees. Anything it touches is not merely warmed, it is flash vaporized. The delicate cold molecular clouds that are the essential nurseries for starbirth, those beautiful nebulae of dust and hydrogen gas, would be instantaneously and utterly annihilated upon contact. To form a star, you need a region of space that is cold, dense, and crucially calm. You need a gentle gravitational collapse where a pocket of gas undisturbed can begin to pull itself together over millions of years, its own gravity slowly winning the battle against outward gas pressure. It is a process of quiet accumulation, a dance of gravity and matter. The jet represents the most violent possible opposition to this process. It is a supersonic tidal wave of plasma crashing through the galactic medium. The turbulence it creates is not like a gentle breeze. It is a galactic hurricane, a shock wave that propagates through space heating and dispersing any nascent cloud of gas it encounters. It shreds the delicate filamentary structures of star-forming regions, blowing them apart like dandelion seeds in a gale. Where a jet passes, it leaves behind a wake of heated, diffuse, chaotic gas, the exact opposite of the conditions required for a single star, let alone a cluster of them, to ever form. It actively scours the galaxy of its raw star-making fuel. But perhaps the most insidious weapon in the jet's arsenal is not its heat or its kinetic fury, but an invisible scourge, its radiation. A black hole's jet is one of nature's most efficient particle accelerators. As electrons and protons are whipped along the magnetic field lines at relativistic speeds, they are forced to spiral, and in doing so, they scream. They emit a constant, powerful and deadly beam of what we call synchrotron radiation. This is not the gentle, life-giving light of a star. This is a torrent of high-energy photons, X-rays and gamma rays, the most destructive forms of light in the universe. This radiation is a sterilizing bath that floods the jet's path for thousands of light years in every direction. It acts as a form of cosmic chemotherapy, stripping atoms of their electrons, shattering the fragile molecular bonds that hold complex molecules together and ensuring that the chemistry for life, and even the chemistry for star formation, cannot proceed. Any region of a galaxy unfortunate enough to lie in the path of one of these jets is effectively rendered a cosmic dead zone. We have seen the evidence for this across the sky. We have observed galaxies where the supermassive black hole's jets are actively pushing vast bubbles of hot gas, clearing out the galactic halo and preventing fresh cold gas from cooling and falling into the galaxy to form new generations of stars. This process, known as AGN feedback, is one of the key reasons why the largest galaxies in the universe eventually stop creating stars. The monster at their core, through its violent feeding process, effectively starves the rest of the galaxy into submission. The jets act as a galactic thermostat, a self-regulating mechanism that throttles star formation, preventing the galaxy from growing too large too quickly. It's a breathtakingly elegant system on a cosmic scale, but its mechanism is one of pure, unadulterated violence. We see this played out in spectacular fashion in galaxies like Hercules A, where the jets have inflated two enormous ghostly lobes of radio-emitting plasma that dwarf the visible galaxy itself, a colossal monument to the power of the central engine. We see it in Cygnus A, a radio galaxy whose jets terminate in brilliant hotspots, places where the beam is slamming into the intergalactic medium with the force of trillions of hydrogen bombs detonating every second. We see it in the famous image of Messier 87, where the Hubble Space Telescope captured a beautiful knotted stream of blue light synchrotron radiation, stretching for 5,000 light-years from its core, a visible testament to this process of sterilization. The jet was therefore an open and shut case. It was the antithesis of a stellar nursery. It was a cosmic sandblaster scouring its parent galaxy of the very ingredients needed for birth. It was too hot, too turbulent, too radioactive. To suggest that a star could form within this river of fire would have been until very recently a scientific absurdity. It would be like suggesting a candle could remain lit in the heart of a thermonuclear explosion, or that a snowflake could survive a journey through the sun. The physics was clear, the observations were consistent, and the conclusion was inescapable. Black hole jets are where stars go to die, not where they are born. For more than a generation of astronomers, this was not a theory, but a foundational truth of astrophysics, a cornerstone of our understanding of how galaxies live and die. The rules of the universe we thought were written. The roles were cast. The black hole was the destroyer, the jet its weapon, the cold dark molecular clouds the victims. This clear, elegant and violent picture of the cosmos defined our place within it, and explained the grand sweeping evolution of the universe, from the Big Bang until today. It was a story that made perfect sense. But the universe, it seems, has little regard for our stories. It delights in paradox, thrives on complexity, and hides its most profound secrets in the very places we are told not to look. For deep within the heart of one such galactic maelstrom, in the unrelenting glare of a cosmic blowtorch, a telescope pointed to a place where nothing should have been able to grow. And it saw the impossible. It saw a flicker of creation. A hint that inside the very engine of destruction a new rule was being written. A suggestion that even in the most hostile place we have ever discovered life of a stellar kind finds a way. And so we were left with a portrait of cosmic annihilation. A vision of monolithic power so absolute, so fundamentally hostile to creation, that it seemed to carve a sterile void through the heart of its own galaxy. For decades our models painted this stark and unambiguous picture of the black hole's jet, portraying it as a monolithic force of sterilization that scoured its host galaxy clean of the very ingredients for new life. It was a story that made perfect, brutal sense, a story that was elegant in its simplicity, and a story that, as our instruments grew more sensitive, was beginning to show the faintest, most unsettling of cracks. The universe, it turns out, rarely adheres to the clean lines of our assumptions. It writes its epics in the margins, in the footnotes, in the data we attempted to dismiss as mere noise. The first hints were not a sudden dramatic revelation, but a quiet, persistent whisper that refused to be ignored. They came from the deepest images our telescopes could capture from long exposure observations staring for hundreds of hours into the apparent emptiness surrounding these celestial blowtorches. Astronomers expecting to see only the smooth, featureless glare of the jet itself and the shocked ionized gas it was ploughing through began to notice something else. Something clumpy. Faint ethereal clouds of gas seemed to hang in the vicinity of the jet like mist clinging to the edge of a raging bonfire. This was profoundly strange. The sheer velocity and temperature of the jet's passage should have dispersed any such clouds in an instant, blowing them apart like dandelion seeds in a gale. Yet there they were, ghostly apparitions on the edge of the inferno, surviving where nothing should survive. It was the light from these phantoms that truly deepened the mystery. When we analyze light, we are performing a kind of cosmic archaeology, breaking it down into its constituent colors, its spectrum to read the chemical and physical story of its source. The light from the jet itself told a familiar tale of violence. It was dominated by signatures of atoms, stripped of their electrons of matter, superheated to millions of degrees, screaming in the X-ray and radio frequencies. This was the signature of a plasma, a testament to the raw, untamed power of the black hole's engine. But from those faint, clumpy regions nearby, Another story was being told. Hidden beneath the overwhelming roar of the jet spectrographs detected the faintest, most delicate of signals, the gentle emission from neutral hydrogen, and even more impossibly the spectral fingerprint of molecular gas. This was not the light of something being destroyed. This was the light of something cold. It was the ghost of hydrogen's song, a lullaby being sung in the heart of a cataclysm. For an astrophysicist, finding the signature of cold molecular gas next to a relativistic jet is like finding a snowflake perfectly preserved on the surface of the sun. It violates the fundamental rules of the environment. It's a piece of evidence so contradictory, so profoundly out of place, that it forces you to question not just your observation, but your entire understanding of the forces at play. The jet was supposed to be a sterilizer, a great galactic sterilizer, heating and blasting all gas out of the galaxy. Yet here was its potential fuel, its very antithesis seemingly coexisting with the fury. The initial reaction, as is so often the case in science, was skepticism. Perhaps it was a trick of perspective, a background cloud billions of light years behind the jet that just happened to align with our line of sight. Or maybe it was foreground gas in our own Milky Way, a local contaminant in the data. Astronomers ran the checks, meticulously calculating the odds of such a chance alignment. They measured the velocity of the gas, its redshift, to see if it was moving with the distant galaxy. Time and time again the results came back, each one more confounding than the last. The cold gas was no illusion. It was there at the same distance, seemingly moving in concert with the outflow. It was a part of the system. The contradiction was real. The snowflake was against all logic, surviving on the edge of the furnace. This was the first great puzzle, the first clue that our grand narrative of destruction was missing a crucial chapter. To understand the sheer depth of this paradox, to truly grasp why this discovery sent such shockwaves through the astronomical community, we must leave the violence of the black hole behind for a moment. We must travel to a different corner of the cosmos, to a place of profound quiet, of deep cold, and of patient, slow creation. We must journey into the heart of a stellar nursery. These are the sanctuaries of the universe, vast sprawling clouds of interstellar gas and dust so immense that our entire solar system would be but a grain of sand lost within their swirling depths. We call them giant molecular clouds, and they are the womb of stars. From a distance they appear as dark, empty patches against the glittering tapestry of the Milky Way voids in the river of starlight. But this darkness is an illusion. They are dark not because they are empty, but because they are incomprehensibly dense with the raw materials of creation. The dominant ingredient is hydrogen, the simplest and most abundant element in the cosmos. But here in the frigid, shielded interiors of these clouds, it is not the single-atom hydrogen that populates most of space. Here the temperatures have plummeted to just a few degrees above absolute zero, a cold so profound that atoms move with a dreamlike slowness. In this stillness, two hydrogen atoms can gently approach, overcome their mutual repulsion, and bond together to form a molecule H2 molecular hydrogen. This transformation is the critical first step in birthing a star. A single hydrogen atom finds it very difficult to radiate away heat. But a molecule of hydrogen, with its ability to rotate and vibrate, is a far more efficient radiator. As the cloud begins to feel the gentle, persistent tug of its own gravity, small pockets of it will start to contract. As they contract, they heat up, just as air heats up in a bicycle pump. If this heat cannot escape, it will create an outward pressure that halts the collapse. But the H2 molecules act like a vast, efficient cooling system, radiating that heat away into the cold emptiness of space as infrared light. This allows the collapse to continue a slow, inexorable gathering of matter over millions of years. Dust plays an equally crucial role, acting as a catalyst and a shield. Tiny grains of silicate and carbon, no larger than particles of smoke, provide surfaces for hydrogen atoms to meet and form molecules. They also act as a great cosmic sunshade, absorbing the harsh ultraviolet radiation from distant stars that would otherwise tear the fragile H2 molecules apart. Inside this protected, refrigerated sanctuary, gravity is the patient sculptor. It is not a violent force here. It is a slow, methodical gathering, a process of accumulation that requires stability and time above all else. Over eons, a clump of gas and dust grows denser and denser, pulling in more material from its surroundings. It begins to spin, conserving the tiny amount of angular momentum it started, with flattening into a disk like a potter's clay on a wheel. At the heart of this swirling disk, a central core forms a protostar. It is here that the pressure and temperature finally begin to mount, the core glowing with the heat of its own compression. For millions of years it will continue to accrete matter from the surrounding disk, growing in mass and luminosity until a critical threshold is reached. Deep within its core, the pressure becomes so immense, the temperature so high, tens of millions of degrees, that a miracle occurs. Hydrogen nuclei, which have spent their entire existence repelling one another, are forced together. They fuse. In that instant, a star is born. A self-sustaining thermonuclear furnace is ignited, releasing a flood of light and energy that will push back against the pull of gravity for billions of years. This entire process, this beautiful, intricate symphony of creation, is predicated on a set of non-negotiable conditions. It requires unimaginable cold to allow molecules to form and gravity to win. It requires high density to give gravity a foothold. And it requires above all else a quiescent environment, a cosmic stillness, a haven from the violence of the galaxy, where the delicate process of gravitational collapse can proceed uninterrupted for millennia. Now hold this image in your mind. This fragile cradle, this cold, dark and quiet nursery, where gravity works its patient magic, and place it if you can inside the maelstrom we witnessed earlier. Place it directly in the path of a black hole's jet. The two realities cannot coexist. They are a physical contradiction, a paradox of fire and ice made manifest on a galactic scale. The very existence of one seems to demand the annihilation of the other. Let us count the ways the jet should prevent star formation. First, there is the matter of temperature. The jet is a conduit of plasma heated to millions, sometimes billions of degrees. A stellar nursery requires temperatures of minus 260 degrees Celsius. Bringing a cloud of molecular gas anywhere near this jet should be like tossing a snowball into a blast furnace. The fragile H2 molecules would be instantly shattered, the gas atoms ionized, and the entire cloud would flash vaporize into a superheated plasma in microseconds. The gentle cooling mechanism so essential for gravitational collapse would be utterly and irrevocably destroyed. Then there is the sheer kinetic violence. The material in the jet is travelling at over 99% of the speed of light. The shock waves it generates as it slams into the interstellar medium are among the most energetic events in the universe. A delicate diffuse cloud of gas held together only by its own feeble gravity would stand no chance. It would be subject to forces of turbulence and shear so extreme that it would be shredded into disconnected wisps, its density obliterated, its structure torn to unrecognizable ribbons. The patient gentle collapse required for a protostar to form would be replaced by a chaotic, explosive dispersal. It's like trying to build a house of cards in the middle of a Category 5 hurricane. The very air is too violent for the structure to even begin to form, let alone stand. Beyond the heat and the motion there is the radiation. The accretion disk and the base of the jet form a cosmic searchlight of unimaginable intensity, flooding their surroundings with a torrent of high-energy X-rays and gamma rays. This radiation is ionizing. It strips electrons from atoms with brutal efficiency. We saw how dust grains were needed to shield the inner parts of a molecular cloud from the gentle ultraviolet light of distant stars. That starlight is a candle compared to the thermonuclear floodlight of a quasar. This radiation would penetrate deep into any gas cloud, destroying the molecular hydrogen and superheating the dust, rendering the entire region utterly inhospitable to the delicate chemistry of starbirth. Finally, there is the problem of time. Star formation is a slow, patient process. The initial collapse of a gas cloud can take millions of years. The journey from a protostar to a main sequence star can take millions more. The environment of a black hole jet is defined by chaos and rapid change. It is a flickering, unstable beam that can shift its direction and intensity over timescales far shorter than those required for a star to mature. There is simply no stable, quiet epoch for the slow work of gravity to be done. The cosmic construction site is located in the heart of a perpetual earthquake, a volcanic eruption, and a lightning storm all at once. So this is the profound challenge, the impossible riddle that the data presented to us. The evidence pointed to the presence of cold, dense, star-forming gas. Yet the laws of physics, as we understood them, declared that such a thing was an impossibility. It was a direct confrontation between observation and theory. On one hand, the telescopes gathering the faint ghostly whispers of molecular hydrogen. On the other, every established model of astrophysics screaming that those whispers could not exist. It was clear that our story was incomplete. There was a fundamental piece of the puzzle missing, a mechanism or a condition that we had failed to consider. Was the jet itself more complex than our models allowed? Could it, in some bizarre and counterintuitive way, be protecting these stellar nurseries, or even triggering their formation? Or perhaps was star formation itself more robust, more tenacious, more ingeniously adaptable than we had ever given it credit for? Could life in its most foundational stellar form find a way to bloom, not just in the calmest gardens of the cosmos, but in the very heart of its most violent storms? The simple narrative of creation and destruction had dissolved into a far more complex and tantalizing mystery. The universe was showing us something new, something that defied our expectations, and astronomers knew, with a thrill of anticipation, that they were on the verge of a paradigm shift. They just had to find the next clue. For years, the idea remained a ghost in the machine, a whisper in the complex mathematics of our simulations, an elegant but unproven theory. We had seen the models. We had watched supercomputers trace the intricate dance between a black hole's fury and the fragile clouds of gas that dared to cross its path. The physics suggested it was possible that under the right exquisitely rare conditions, the crushing force of a jet could become not a destroyer but a creator, a cosmic midwife. But a simulation is not a photograph. A prediction is not a reality. The universe is under no obligation to conform to our neatest theories. The question hung in the air at every conference, a challenge passed between astronomers in hushed tones. Where was the proof? Where could we find, among the billions of galaxies scattered across the cosmos, the definitive evidence? The search was for a needle in a haystack the size of the observable universe. We were looking for a stellar nursery in the heart of a hurricane, a fragile cradle of life rocked by the most powerful engine in existence. To find it, we would need to look not just for stars, but for the raw ingredients they are made from. We had to find a place where the jet's influence was undeniable, a laboratory where the experiment was already in progress. Our gaze turned to a spiral galaxy much like our own Milky Way in form, but possessed by a far more violent heart. Lying some 155 million light-years away in the constellation of Indus is a galaxy known as IC 5063. At first glance, it is unassuming. A graceful swirl of stars and dust, a quiet island in the cosmic sea. But hidden within its core, shrouded by immense curtains of gas, a supermassive black hole was awake and feeding. And as it consumed the material spiralling into its grasp, it unleashed a colossal jet of plasma. Unlike the jets we'd seen erupting far out into intergalactic space, this one was different. It was trapped. Fired almost sideways, it was ploughing directly into the dense, cold, dusty disk of its own galaxy. IC 5063 was not just a galaxy. It was a cosmic crime scene, a place where an irresistible force was meeting a very movable object. It was the perfect place to hunt for our ghost. Our first reconnaissance of this turbulent world didn't use eyes that see invisible light. To find the nurseries, we first had to find the building materials. For that, we turned to an array of metallic ears spread across the driest desert on Earth. The Atacama Large Millimeter, Submillimeter Array, or ALMA. This remarkable instrument doesn't see the twinkle of stars. Instead, it listens for the faint cold glow of molecular gas clouds, the very stuff from which stars are born. When ALMA turned its collective gaze towards IC 5063, it began to build a map not of light but of substance. A map of the cold, dark heart of the galaxy. The initial data trickled in, painting a picture of chaos. We saw the vast rotating disk of molecular gas, a reservoir of trillions of suns waiting to be born. And then we saw the wound, a clear, unmistakable path carved through the disk where the jet was tearing it asunder. As predicted, ALMA saw gas moving at incredible speeds, hundreds of kilometers per second swept up in the jet's torrent. This was the destructive force we expected the galactic wind blowing the potential for future stars out into the void. It was textbook negative feedback in action. But as the map grew more detailed, as the hours of observation were stitched together into a single breathtaking portrait, something utterly unexpected began to emerge from the noise, directly in the path of the jet along the turbulent shock front where the plasma beam was slamming into the galactic disk. ALMA detected stillness. Pockets of gas that weren't being blown away. Instead, they were being squeezed. The data revealed incredibly dense compact knots of molecular gas colder and far more concentrated than anything in the surrounding disk. You have to understand the profound strangeness of this discovery. It was like finding calm, deep pools of water on the face of a raging waterfall. The jet this celestial blowtorch was supposed to be heating and dispersing this gas, boiling it away into nothing. Instead, in these specific locations, it appeared to be acting like a cosmic piston, compressing the gas clouds, ramming them together with unimaginable force. These clumps were the first piece of the puzzle, the motive and the opportunity. The jet was providing the pressure the immense sustained squeeze needed to push a gas cloud over the edge. According to our understanding of star formation, when you compress a molecular cloud, you kickstart a process of gravitational collapse. If the cloud is squeezed hard enough, its own gravity will take over, pulling it inward, crushing it down until its core becomes so hot, so dense, that the fires of nuclear fusion ignite. A star is born. The ALMA data showed us the potential. It showed us the pressure cooker. We had found the compressed gas the stellar seeds packed and primed, but were they sprouting? Had any of them actually ignited to answer that? We needed a different kind of eye. We needed to look for the fire itself. We needed the Hubble Space Telescope. With the ALMA map as our guide, we knew exactly where to point Hubble's legendary mirror. We aimed it directly at those mysterious hyper-dense clumps of gas nestled within the jet's path. The request for observation time was a gamble. Hubble is one of the most in-demand scientific instruments ever created, and we were asking it to stare into the heart of a galactic storm, hoping to see the flicker of a cosmic candle. What we were looking for was a very specific signature. The brilliant, fierce, blue-white light of infant stars. When stars are first born, the most massive among them burn with an intensity that is difficult to comprehend. They are stellar titans, O-type and B-type stars that live fast and die young, blazing with a light that can outshine millions of suns like our own. Their ultraviolet radiation is so powerful it acts like a beacon ionizing the gas around them, and causing it to glow in a characteristic shade of red, a spectral fingerprint known as H-alpha emission. Finding that blue light and its associated red glow in those precise locations would be the smoking gun. The data from Hubble came down to Earth not as a beautiful fully formed image, but as a stream of raw numbers. It fell to teams of scientists to process it, to clean it, to calibrate it, to translate the cold, hard data into a picture our eyes could understand. You can imagine the scene. Researchers gathered around a monitor, the culmination of years of work of theory and observation, about to be revealed in a single frame. The first image loaded. It showed the grand sweep of IC 5063's disk, a tapestry of old yellow stars threaded with dark lanes of interstellar dust, and then cutting across it the chaotic glowing filament of the jet's path. They began to zoom in, pushing deeper into the image, targeting the coordinates ALMA had provided. They moved past the foreground stars of our own galaxy, past the swirling arms of IC 5063 itself, and into the turbulent zone where gas and plasma collided. And there they were. At first, just a few pixels. But as the image resolved, they became undeniably clear. A string of brilliant blue-white knots of light perfectly aligned with the propagation of the jet like pearls on a string. Each pinpoint was a cluster of newborn stars, dozens, perhaps hundreds of them blazing together. They were exactly where the ALMA data said the compressed gas should be. They were young, no more than a few million years old, mere infants on a cosmic timescale. And they were embedded deep within the outflow, surrounded by the telltale red glow of ionized hydrogen. It was breathtaking. It was the smoking gun. For the first time, we were not looking at a simulation or a graph of spectral data. We were looking at a photograph of stars being born inside a black hole's jet. The ghost in the machine had materialized. The theory had been made real. The initial reaction within the community was a mix of sheer astonishment and profound skepticism. It seemed impossible. How could the delicate process of star formation, which requires a relatively calm and stable environment for a gas cloud to gently collapse, possibly happen here? This was one of the most violent places in the universe. The jet is a torrent of particles moving at near the speed of light, carrying immense energy. The shock waves, the turbulence, the radiation. It should all conspire to rip these nascent stellar cocoons to shreds long before they could ever form a star. The first challenges came swiftly. Could this just be a coincidence? A chance alignment? Perhaps these were older star clusters from the galactic disk that just happened to lie along our line of sight to the jet. This was a crucial question, a test of the discovery's integrity. The team had to prove beyond any reasonable doubt that these stars were not just near the jet, but were kinematically linked to it, that they were born of it. To do this, they turned to another powerful tool of astronomy spectroscopy. By splitting the light from these new star clusters into its constituent colours, its rainbow astronomers can measure their motion with incredible precision. If the stars were simply part of the galaxy's disk, their velocity should match the slow, orderly rotation of the disk itself. But if they were truly formed within the jet, they should be moving with the jet caught in its powerful current. For this, they used instruments like the Very Large Telescope's Muse instrument, a spectrograph that can take thousands of spectra at once, building a 3D picture of an object's light and motion. The results were unequivocal. The light from these young blue stars was massively redshifted and blue-shifted, revealing motions of hundreds of kilometers per second relative to the rest of the galaxy. They were moving far too fast to be part of the stable galactic disk. Their velocity matched perfectly the velocity of the outflowing gas that ALMA had measured. They were not a chance alignment. They were passengers on the storm born in the tempest and now riding it out into the galactic halo. This confirmation sent shockwaves through the fields of astrophysics and cosmology. For decades we had operated under a simple, elegant assumption that the jets from supermassive black holes were purely destructive forces. They were the universe's ultimate kill switch, a self-regulating mechanism that prevented galaxies from growing too large by blasting away their reserves of star-forming gas. This was the foundation of our models of galaxy evolution. We called it negative feedback. The black hole grows, launches a jet, the jet clears out, the gas star formation halts, the black hole runs out of fuel, and the system stabilizes. It was neat. It was tidy. It explained so much about why we see galaxies the size that we do. But the discovery in IC 5063 turned this entire picture on its head. It revealed a stunning new layer of complexity, a cosmic paradox. The very mechanism that we believed only ever halted star formation could, under the right circumstances, actually trigger it. This wasn't just negative feedback anymore. This was something else entirely. Something more nuanced, more intricate. We had found direct, irrefutable evidence of positive feedback. The jet was still clearing out gas from the galaxy on a massive scale, acting as a brake on overall star formation. But along the way, in localized pockets, its immense power was being repurposed, channeled into creating new generations of stars in places we never thought possible. Imagine a wildfire raging through a forest. Its primary role is one of destruction, clearing vast tracts of land. But in its wake, the heat can cause certain types of pine cones to burst open, releasing their seeds onto the newly fertile ash. The destructive force in a localized and specific way becomes a catalyst for new life. This is what we were seeing in ISA 5063. The black hole's jet was a galactic wildfire, and we had just found its first star-bearing pine cones. The implications began to ripple outward. These stars, born in the outflow, are on a one-way trip out of the galaxy. They will enrich the intergalactic medium with heavy elements when they eventually die, seeding the void with the building blocks for future cosmic structures. This process could help explain the mysterious presence of metals found in the vast empty spaces between galaxies. Furthermore, it forced us to reconsider the role of black holes in their entirety. They were not just cosmic drains or simple engines of destruction. They were sculptors. Their influence was a far more delicate and multifaceted dance than we had ever appreciated. They could prune, and they could plant. They could stifle, and they could spark. They were an integral, active, and creative part of the cosmic ecosystem. The discovery in IC 5063 was a watershed moment, a turning point that transformed our view of the relationship between a galaxy and its central monster. We had found the smoking gun, and it had fired a bullet straight through our old assumptions. But this revelation only opened the door to an even deeper, more profound mystery. We had the evidence, we had the photograph, we knew with certainty that it was happening. But we still didn't truly understand. How? How could something so fragile as a stellar nursery possibly survive its birth in the heart of such unimaginable violence? And so the evidence became undeniable. The spectral fingerprints were a perfect match. The light signature, an unambiguous declaration of stellar birth. There within the violent incandescent outflow of a supermassive black hole, an engine of pure destruction, something impossible was happening. New suns were being born. The discovery left the astronomical community in a state of stunned reverence, a moment of profound recalibration, where a fundamental law of the cosmos seemed to have been flagrantly broken. The question that had fueled the initial search, the hesitant what if, was now answered. But in its place, a far more challenging, more urgent, and perhaps more fundamental question now thundered across the discipline. How could life-giving cradles of creation exist within the universe's most efficient shredder? The very idea felt like a paradox sculpted from plasma and light. For generations we had understood these galactic jets as sterile forces, cosmic blowtorches that would heat, ionize, and blast away any nascent cloud of gas, long before it could ever dream of collapsing into a star. The environment inside one of these outflows is a physical nightmare. Temperatures soar to millions of degrees hot enough to strip electrons from their atoms. The material itself is moving at a significant fraction of the speed of light, a relativistic hurricane that should tear any delicate structure to pieces. The radiation is so intense, a torrent of X-rays and gamma rays, that it should photo-dissociate molecules, breaking the chemical bonds necessary for the complex cooling processes that precede star formation. In this maelstrom, a gentle condensing cloud of hydrogen should have the same chance of survival as a snowflake in a furnace. Yet the stars were there. The data was irrefutable. Our understanding was not wrong, but it was profoundly incomplete. Science had to abandon its certainty and embrace the chaos to look into the heart of that destructive furnace and find the hidden forge. The quest for an answer pushed theorists to their absolute limits, forcing them to build new models of the universe from the ground up, this time with a seemingly impossible outcome as their starting point. Out of this intense intellectual crucible, a leading and astonishingly elegant hypothesis began to take shape, a concept known as jet-induced star formation. The theory's central premise is as poetic as it is powerful. It proposes that the jet's destructive force is not an impediment to star birth, but its primary catalyst. It suggests that nature, in its infinite complexity, had devised a way to weaponize the destruction itself, turning the galactic scale sword into a celestial plowshare. To understand this, you have to reimagine the jet not as a smooth, uniform column of energy, but as a turbulent, messy, and structured river of plasma. It isn't a laser beam. It's more like the torrent of water bursting from a colossal dam filled with eddies, vortices, and powerful shock waves that propagate outwards. The jet slams into the surrounding interstellar medium, the tenuous gas and dust that fills the space between stars in a galaxy. This is not a gentle merger. It is a cataclysmic collision on a scale that dwarfs our comprehension. The leading edge of the jet acts like a cosmic snowplow, gathering up vast quantities of ambient gas and dust, creating a dense, turbulent, and superheated sheath around the primary outflow. It is here, in this chaotic boundary layer between the jet's fury and the galaxy's calm, that the miracle begins. The key lies in the shock waves. Imagine a supersonic aircraft breaking the sound barrier. It creates a powerful shock front, a sudden violent change in pressure that you hear as a sonic boom. Now scale that concept up to an unimaginable degree. The plasma in the black hole's jet, moving at near light speed, creates shock fronts of such immense power that they can compress the interstellar gas with the force of 1 billion exploding suns. This is the first critical step. Star formation at its core is a battle between two fundamental forces, the outward push of gas pressure and the inward pull of gravity. For a star to be born, gravity must win. This requires the gas to be incredibly dense, its atoms and molecules packed so tightly together that their collective gravitational attraction becomes overwhelming. In a normal stellar nursery like the Orion Nebula, this process is slow and gentle, taking millions of years as a cold giant molecular cloud slowly succumbs to its own weight. But in the jet there is no time for gentle persuasion. The process requires a hammer, not a whisper. The shock waves are that hammer. As a shock front propagates through the sheath of accumulated gas, it acts like a gravitational vice. It doesn't just push the gas, it violently squeezes it, increasing its density by factors of thousands, or even hundreds of thousands in an astonishingly short period of time. It takes a diffuse fluffy cloud and instantaneously compacts it into a dense compact knot of material, a potential stellar embryo. This is the destructive force being repurposed. The very energy that should have dispersed the cloud is instead used to compress it to the brink of gravitational collapse, creating the raw material for a new star. But this violent compression introduces a new and formidable problem, a paradox within the paradox. When you compress a gas, you heat it up. This is a fundamental law of thermodynamics, one you experience every time you pump air into a bicycle tire and feel the pump get warm. In the case of the jet-induced shocks, the heating is not trivial. The gas is flash heated to millions of degrees, and hot gas creates immense outward pressure. It wants to expand to fly apart, not to collapse further. A superheated, compressed knot of gas is not a protostar. It's a bomb waiting to go off. For gravity to win its tug of war, this intense heat, this thermal energy must be radiated away, and it must be done with extraordinary efficiency. The cloud must cool down, and it must do so faster than it can re-expand. This cooling conundrum became the central focus of the theoretical models. How could a pocket of gas trapped in a celestial furnace possibly manage to cool itself? The answer lies in the very material the shockwave compressed. The interstellar medium is not just pure hydrogen. It is seeded with heavier elements forged in the hearts of previous generations of stars. It contains carbon, oxygen, and silicon, which can form complex molecules and dust grains. These elements and molecules are vastly more efficient at radiating away heat than simple hydrogen atoms. As the shockwave crushes the gas, these heavier elements are slammed together. The energized electrons in these atoms jump to higher orbits and then cascade back down, releasing their excess energy not as heat, but as photons of light. The cloud literally begins to glow, broadcasting its thermal energy out into space in the form of infrared and microwave radiation. It becomes its own radiator, a beacon of cooling in a sea of fire. This is a frantic race against time. On one side, you have the thermal pressure of the superheated gas trying to explode outwards. On the other, you have the relentless pull of gravity strengthened by the initial compression trying to pull it all inwards. And acting as the crucial mediator is this process of radiative, cooling a desperate shedding of energy that weakens the outward push of pressure. If the cooling is fast enough, if the cloud can shed its heat before it has a chance to rebound from the shock, the balance tips. The inward pull of gravity becomes the dominant force. The point of no return is crossed. This is the moment of genesis. The dense cooling knot of gas, now gravitationally bound, begins to collapse under its own weight, a process that is now irreversible. It continues to shrink to heat up again, but this time the heat is generated by gravitational potential energy, being converted into thermal energy at its core, not by an external shock. The core becomes hotter and denser, pulling in more and more material from its immediate surroundings. Eventually, the pressure and temperature in the very heart of this collapsing cloud reach the critical threshold of 10 million degrees Celsius. At that point, a new fire is lit. Nuclear fusion ignites. Hydrogen atoms begin to fuse into helium, releasing a torrent of energy that pushes outwards, finally halting the gravitational collapse and establishing a stable equilibrium. A star is born, not in a placid dark nebula, but forged in the crucible of the galaxy's most violent phenomenon, a fledgling sun ignited by the breath of a monster. This entire process from shockwave compression to nuclear ignition happens at a blistering pace, perhaps in less than 1 million years, a mere blink of an eye in cosmic terms. It is star formation on overdrive, a high-pressure, high-stakes version of the process that is both terrifying and beautiful to contemplate. This theoretical model, jet-induced star formation, was a masterpiece of creative physics, a plausible and mathematically sound explanation for an observation that had seemed impossible. But a beautiful theory is not enough. Science demands verification. It demands proof that this intricate dance of shock waves, cooling and collapse, isn't just an elegant fiction existing on a blackboard. The challenge was immense. We cannot fly a probe into a black hole's jet to take measurements. We cannot watch the process unfold in real time over thousands of years. The only way to test this hypothesis to see if it truly works was to build a universe in a box. This is the domain of computational astrophysics, one of the most demanding and powerful fields in modern science. It required the world's largest supercomputers machines capable of performing quadrillions of calculations per second, running for months on end. The goal was to create a digital simulation so complex and so faithful to the laws of physics that it could accurately model the maelstrom around a supermassive black hole. The task was nothing short of breathtaking in its ambition. The programmers and physicists had to write code that accounted for everything. They had to model the crushing force of gravity. They had to simulate the intricate and often counterintuitive laws of magnetohydrodynamics, the physics of electrically charged fluids like plasma, which governs the shape and behavior of the jet itself. They had to include thermodynamics tracking how gas heats and cools under extreme pressure. They had to incorporate radiation transport, calculating how photons travel through and interact with the gas, a crucial component for the cooling mechanism. They even had to include the complex chemistry of molecule and dust formation, the very ingredients that make rapid cooling possible. Creating this virtual cosmos is like painting a masterpiece with mathematics. The simulation begins with a digital galaxy, a vast grid containing billions of individual points, each representing a parcel of gas with specific properties like temperature density and velocity. At the center, they place a virtual supermassive black hole, programmed to behave exactly as Einstein's equations predict. Then they switch it on. The simulation comes to life. The black hole begins to accrete digital matter, and from its poles a jet of high-energy plasma erupts, tearing through the simulated galaxy. The scientists can do what is impossible in reality. They can pause the universe. They can fly through the jet zoom in on a single shock front and measure the temperature and density of a gas cloud as it is being compressed. They can watch frame by agonizing frame as these virtual clouds struggle against their own internal heat, desperately radiating their energy away. For the teams running these simulations, it was a period of intense anticipation. The initial models were too simple. They would show the gas being compressed, but then it would immediately fly apart, too hot to collapse. The physics was incomplete. They refined the code, adding more complex cooling functions, a more accurate treatment of turbulence, a more detailed understanding of the jet's magnetic fields. They ran the simulations again and again, each run consuming millions of hours of processing time, a testament to the intractable difficulty of the problem. They were searching for a ghost in the machine, a digital flicker that would confirm their theory. They were looking for the birth of a virtual star. And then, after years of painstaking work, it happened. Deep inside the turbulent simulated sheath of a galactic jet, a knot of gas was hit by a shock wave. The simulation showed its density skyrocketing, its temperature flaring up to millions of degrees. But then, as the new, more sophisticated cooling physics kicked in, the temperature began to plummet. The on-screen data scrolled with numbers that showed the balance of forces tipping. The outward thermal pressure dropped, while the inward pull of gravity held steady, then grew stronger. The knot of gas began to collapse. It shrank, spun faster, and in its core a single point on the vast computational grid crossed the threshold for nuclear fusion. The code registered the event, flagging it with a marker that, for the scientists watching, was as electrifying as any signal from a real telescope. A star had just been born in their digital universe. They let the simulation run, and more stars began to form, clustered along the edges of the jet, appearing like pearls on a string, their locations and properties a stunning match for the real observations that had started this whole quest. It was a moment of profound triumph, the closing of a loop between observation theory and verification. The simulations proved that it was not only possible, but under the right conditions almost inevitable. The destructive fury of the jet, when properly channeled, could indeed become a prolific engine of creation. The model held, but in solving one mystery, it opened the door to a dozen more. What kind of stars are these forged so quickly and in such violence? Are they different from the stars born in quiet nebulae? Do they have a shorter, more brilliant lifespan, living fast and dying young? And what does this newly discovered mode of star formation mean for the evolution of galaxies as a whole? We had found the mechanism, the how, but we were only just beginning to grapple with the deeper implications of what it means when the universe's darkest hearts learn how to create their own light. A theory, no matter how elegant, remains a ghost in the machine of science until it can face the cold, hard light of observation. The idea of stars igniting within a black hole's fury was just such a ghost, a beautiful, almost heretical speculation. For generations we had painted these jets as cosmic scourges, as galactic sterilizers that blast through nascent stellar nurseries, scattering the seeds of creation before they can ever take root. Yet the universe had presented us with a profound contradiction, a string of impossible blue lights shining defiantly from within the storm. To prove that these were not just a cosmic mirage, we had to move beyond hypothesis. We had to gather proof. And so we turned our greatest eyes back to the heavens, not just to look, but to interrogate the light itself. Using the European Southern Observatory's Very Large Telescope, a quartet of colossal mirrors nestled high in the arid stillness of the Atacama Desert, astronomers began a meticulous cosmic inquest. Their target was a galaxy designated IC 5063, a place where a supermassive black hole's jet was slicing directly through a dense wall of interstellar gas. This wasn't a gentle interaction, it was a titanic collision, a place where the universe was being torn apart and perhaps remade. With the telescope's multi-unit spectroscopic explorer or muse, they could do more than just take a picture. They could dissect the light from every single point in their field of view, breaking it down into its constituent colours, its chemical fingerprint. What they were searching for was the signature of a specific kind of chaos. Not the smooth, predictable rotation of a placid galactic disk, but the turbulent, violent motion of gas caught in a maelstrom. And they found it. The spectral lines of the hydrogen gas, which should have been uniform, were instead smeared and twisted. In some regions, the gas was hurtling towards us at hundreds of kilometers per second, while in adjacent pockets it was screaming away with equal fury. This was the unmistakable signature of extreme turbulence, a cauldron of churning energy precisely where the jet impacted the molecular cloud. The jet was acting like a colossal cosmic blender, whipping the quiescent gas into a frenzy. This was the first piece of the puzzle, a confirmation of the violent conditions necessary for our impossible theory. The engine of chaos was real, but turbulence alone does not make a star. You need something more. You need compression. For a star to be born, a vast diffuse cloud of gas and dust must be squeezed down, crushed by gravity, until its core becomes so hot and dense that nuclear fusion ignites. The jet, we theorized, was the cosmic piston providing that initial violent squeeze. To find evidence of this, we look to another marvel of engineering, the Atacama Large Millimeter, Sub-Millimeter Array, or ALMA, a sprawling network of 66 precision antennas. ALMA doesn't see the visible light of stars. Instead, it peers into the cold, dark universe, detecting the faint microwave glow emitted by the universe's most frigid dust and gas, the very substance from which stars are made. ALMA allows us to see into the heart of stellar nurseries, to witness the delicate dance of gravitational collapse in its earlier stages. When ALMA was pointed at the same turbulent region in I-5063, the picture it painted was breathtaking. It revealed dense, clumpy knots of carbon monoxide gas, a tracer for the cold, molecular hydrogen that is the primary fuel for star formation. These weren't just random condensations. They were concentrated compact cores lined up along the edges of the jet's path like beads on a string. ALMA's data showed that these clumps were gravitationally unstable, teetering on the very brink of collapse. They were cosmic eggs incubated not by gentle gravity over eons, but shock-heated and compressed by the jet's relentless advance. The evidence was mounting. We had found the chaotic energy source with the VLT and now with ALMA we had found the compressed star-forming fuel. We were witnessing the crime scene identifying the weapon, and finding the victim's fingerprints all over it. Still, the ultimate proof had to come from the stars themselves. Were there genuinely young stars there? For this we needed the unparalleled vision of the Hubble Space Telescope. Suspended in the blackness of orbit, free from the blurring veil of Earth's atmosphere, Hubble could resolve the individual points of light within this distant galactic tempest. Its gaze revealed what ground-based telescopes could only hint at: a chain of brilliant blue-white stars, blazing with the fierce ephemeral light of youth. These were not old placid suns. Their intense blue colour was the telltale sign of massive hot young O and B-type stars, stellar titans, that burned through their fuel in a cosmic blink of an eye just a few million years. Their very existence was a temporal paradox. They had to have been born recently because they simply do not live long enough to have migrated there from somewhere else. They were born right there inside the inferno, precisely where the theory predicted they would be. This alignment was the linchpin. The VLT showed the turbulent motion, ALMA showed the compressed gas on the verge of collapse, and Hubble showed the newborn stellar giants still wrapped in their gaseous cocoons, standing as luminous monuments to their violent birth. The observations from three of humanity's most powerful astronomical instruments, each observing a different facet of the universe, all converged on a single astonishing conclusion. The ghost in the machine had solidified into a tangible reality. The black hole's jet was not just a harbinger of destruction, it was also a midwife to creation. Yet even with this cascade of observational evidence, a crucial question lingered. Could we truly understand the physics of this bewildering process? Watching it from billions of light years away is one thing. Comprehending the intricate dance of plasma gravity and gas dynamics is another entirely. To bridge this gap, to move from observation to understanding, we had to build the storm ourselves. We had to recreate the universe in a box. This is the realm of astrophysical simulations, one of the most powerful tools in the modern astronomer's arsenal. Inside the silent humming cathedrals of supercomputing, we can construct entire galaxies from the fundamental laws of physics. We pour in the digital hydrogen and helium seed, the phantom gravity that will bind it all together, and at the heart of our simulated cosmos, we awaken the beast. In these virtual laboratories, time itself becomes malleable. We can watch the slow, majestic evolution of a galaxy, a process that takes billions of years in reality, unfold on our screens in a matter of weeks. For this specific problem, teams of astrophysicists designed what they called the jet in a cloud experiment. They would not simulate an entire galaxy, but focus with microscopic precision on the crucial moment of impact. They began by coding a vast, turbulent cloud of interstellar gas, endowing it with the properties of density and temperature measured by our telescopes. They let it settle into a state of fragile equilibrium, a place where gravity was gently pulling inwards, but the gas pressure was pushing back, preventing widespread collapse. This was a stellar nursery awaiting a region ripe with potential, but lacking the trigger to begin the process of creation. Then, with a single command line, they unleashed the jet. From one edge of their computational box, they fired a beam of high-energy particles, a digital recreation of the relativistic outflow from a supermassive black hole. It was a celestial blowtorch aimed at a powder keg. What we witnessed next, as the supercomputers churned through quadrillions of calculations per second, was not the simple apocalypse we might have expected. The jet did not merely vaporize the cloud or blast it into oblivion. The process was far more subtle, far more intricate, and infinitely more creative. As the jet's shockwave, a moving wall of immense pressure and temperature, slammed into the denser gas cloud, it created a chaotic two-phase medium. The outer layers of the cloud were indeed heated and stripped away, evaporated into a tenuous million-degree plasma that flowed along the jet's axis. This was the destructive face of the black hole, the quenching process we had always known. But deeper inside the cloud, the story changed. The shockwave didn't just heat, it compressed. It acted like a cosmic snowplow, gathering up material and ramming it into the cloud's denser, colder heart. The simulations showed the formation of intricate filaments and sheets of hyper-compressed gas structures far denser than anything that could have formed through gravity alone. Pockets within the cloud that were once stable were now squeezed past their breaking point. their self-gravity suddenly amplified and overwhelming their internal pressure. The simulation blossomed with points of runaway collapse. All across the leading edge of the shock front, the code signaled the birth of sync particles, the computational shorthand for newly formed protostars. The simulation was spontaneously violently giving birth. We could fly our virtual camera through the storm, witnessing what no telescope could ever resolve. We could see the bow shock of the jet wrapping around a dense clump, squeezing it from all sides like a cosmic fist. We could watch as the intense radiation from the shock front cooled behind it, allowing the compressed gas to rapidly shed its heat and collapse even faster. The simulation revealed that this method of star formation is incredibly efficient, converting a much larger fraction of the gas cloud into stars than the gentle, slow process that occurs in spiral arms. It is a form of celestial shock and awe, a brutal but wildly effective way to build a new generation of suns. The virtual universe, governed only by the laws of physics, had independently rediscovered the phenomenon our telescopes had observed. The theory was no longer just plausible, it was now computationally inevitable. This convergence of observation and simulation gave us the confidence to ask an even deeper question. If these stars are born in such an extraordinary way, are they themselves extraordinary? A star's identity, its mass, its lifespan, its ultimate fate is written in the conditions of its birth. A star born in the serene, dusty arms of a galaxy, like our own Milky Way, inherits a rich chemical legacy, a history of billions of years of stellar recycling. But these jet-born stars, these children of chaos, would have a very different heritage. Our simulations suggested that the initial mass function, the statistical distribution of stellar masses at birth, would be dramatically skewed. In a normal stellar nursery, for every one massive star, nature creates hundreds of smaller, long-lived stars like our Sun. But in the violent compression of a jet-induced shockwave, the conditions favour fragmentation into much larger pieces. The simulations predicted a top-heavy distribution, a stellar population dominated by massive, brilliant O and B-type stars. This was a stunning prediction, and it perfectly matched what Hubble had seen, a profusion of brilliant blue giants with a noticeable scarcity of smaller yellow and red stars. They were a generation of titans with few commoners. Their chemical composition would also tell a unique story. The jet is launched from the immediate vicinity of the black hole, a region fed by pristine gas falling into the galactic core from the cosmic web, or from the less processed gas of the galactic halo. This gas is often metal-poor, meaning it has a lower concentration of elements heavier than hydrogen and helium compared to the gas in the star-forming disks of galaxies. Stars forged from this material would be born with a more primordial chemical signature. Their spectra would bear the mark of their unusual conception, setting them apart from the metal-rich stars of the galactic plane. Finding such a chemical anomaly in these stars would be akin to finding a polar bear in the Sahara, an unambiguous sign that it originated from a very different environment. Future observations with the James Webb Space Telescope, with its incredible sensitivity to infrared light and its ability to perform detailed spectroscopy, are poised to test this very prediction. And what of their environment? These stellar orphans are born into an existence of profound isolation and peril. Unlike stars in a typical cluster which co-evolve in a relatively stable gravitational embrace, these stars are strung out along the jet's trajectory. They are born on the move, imbued with the high velocity of the shockwave that created them. They are likely to be rogue stars from the moment of their birth, flung out into the galactic halo, on long looping orbits destined to travel alone through the intergalactic dark. They are born into a crossfire, bathed in the harsh X-ray and gamma-ray radiation from the jet itself, a hostile environment that would strip the atmospheres from any fledgling planets that might dare to form around them. Life as we know it would find little sanctuary here. These are stars born not to nurture, but to burn brightly and die young, a brief brilliant flash of defiance against the darkness. We had arrived at new, more nuanced understanding. The picture of the supermassive black hole as a monolithic agent of galactic death was dissolving, replaced by a far more complex and fascinating portrait. We were looking at a cosmic engine that governs its domain through a dynamic, self-regulating feedback loop. The black hole feeds on the galaxy's gas, and in doing so it launches these colossal jets. Where the jets tear through low-density regions, they heat the gas and prevent new stars from forming, a process we call negative feedback. This is the destructive side, the quenching mechanism that can cause a galaxy to prematurely age and die. But as we now understood where that same jet slams into a dense, massive cloud of cold gas, the outcome is inverted. The immense pressure triggers a ferocious burst of star formation. This is positive feedback, the creative impulse. The black hole, in the very act of its feeding, is planting new seeds of light and matter throughout its galactic kingdom. It is a cosmic gardener pruning the diffuse branches, while simultaneously forcing blooms in the densest thickets. The jet is not merely a weapon. It is a sculptor's tool, carving out vast cavities in the interstellar medium with one hand while compressing and igniting new constellations with the other. This duality transforms our entire perception of how galaxies live and breathe. It reveals a universe of intricate connections where the largest and most violent phenomena are directly linked to the birth of the smallest, most luminous objects. The very engine that can shut down a galaxy's future is also capable of writing its next chapter, seeding the halo with a generation of massive chemically distinct stars that will live die and enrich their surroundings, changing the destiny of their host galaxy. The paradox was resolved. The monster at the heart of the galaxy was not just a monster after all. It was a parent, a creator, a formidable force of cosmic renewal, locked in an eternal, violent and profoundly creative dance with the galaxy it calls home. And in understanding this dance, we have taken one more step towards understanding our own place within this grand, interconnected cosmos. And so we arrive here at the precipice of a transformed cosmos. The journey we have taken together from a perplexing scatter of starlight to the churning heart of a galactic furnace has delivered us to a conclusion that is as profound as it is unexpected. We are left to confront a universe far more intricate, more interconnected and more astonishingly creative than we ever dared to imagine. The image of the black hole, that silent, sombre monolith of physics, the ultimate symbol of cosmic finality, has been irrevocably shattered. In its place stands a new paradoxical entity, a destroyer, yes, but also a progenitor. A cosmic heart that not only consumes, but also pumps the very lifeblood of creation back into the void. This is not merely an addendum to our astronomical textbooks, it is a fundamental rewriting of the central chapters of galactic evolution. For decades we saw the relationship between supermassive black holes and their host galaxies as an adversarial one, a cosmic battle of wills. The black hole's jets were the ultimate weapon of suppression, a celestial blowtorch scouring the galaxy of its star-forming fuel, heating vast clouds of gas until they could no longer collapse under their own gravity to form new suns. This process, known as negative feedback, was our elegant explanation for why the most massive galaxies in the universe mysteriously stopped producing stars, becoming vast, silent cities of aging red suns. It was a tidy, logical theory that cast the black hole as a galactic monarch issuing decrees of sterility from its throne at the galactic centre. It was a story of control, of limitation, of an ending. But the stars we have witnessed, born in fire and fury within the very blast they should have fled, tell a different story. They speak of a positive feedback loop, a mechanism so potent it forces us to reconsider the entire ecological balance of a galaxy. The jet, this torrent of matter moving at nearly the speed of light, is not just a sterilizing wave of heat. It is also a kinetic titan, a stupendous cosmic piston that slams into the diffuse, complacent clouds of interstellar gas. Imagine a shockwave of unimaginable power propagating outwards, compressing the thin, cold hydrogen 1,000-fold, 1,000,000-fold, until pockets of that gas are pushed past the critical breaking point, the gene's instability where their own gravity takes over. The jet in this new narrative is the midwife of stellar birth. It is the forceful hand that squeezes the raw material of the cosmos, igniting the nuclear furnaces of a new generation of stars in places where they had no right to exist. This single discovery provides a stunning solution to a lingering cosmic puzzle. How do galaxies sustain their star formation over billions of years? Perhaps it is not a slow, gentle process, but a dramatic, cyclical one, driven by the very monster at their core. The black hole consumes, matter grows, and in a furious outburst triggers a wave of star formation far out in the galactic halo. Those new stars live, die, and enrich the interstellar medium with the heavy elements forged in their cores, the carbon, the oxygen, the iron necessary for planets and for life. Some of that enriched material eventually finds its way back, spiraling down into the galactic centre, feeding the black hole once more. It is a grand symbiotic cycle, a cosmic breath of inhalation and exhalation, where the black hole is not the villain but the pulsing rhythmic engine driving the entire system forward through cosmic time. It suggests that the growth of a galaxy and the growth of its central black hole are not just correlated. They are profoundly physically intertwined, locked in an eternal dance of creation and consumption. The jet becomes a celestial umbilical cord delivering the necessary energy and pressure to gestate stars in the otherwise barren wilderness of a galaxy's outer reaches. Our perception has been fundamentally altered. We were looking at the fingerprints of a sculptor, and for the longest time we mistook them for the scars of an executioner. This epiphany also reshapes our understanding of the universe's chemical history. Stars are the forges of the elements, the only places in the cosmos where hydrogen and helium are cooked into the heavier materials that constitute our world, our bodies. But getting those elements out of the galactic core and distributing them across tens of thousands of light years has always been a challenge for our models. Supernovae and stellar winds can only do so much. Now we have a new spectacular transport mechanism. The jet acts as a cosmic cannon, dredging up enriched material from the densely packed environment around the black hole and firing it deep into the galactic halo and beyond, seeding the entire galactic ecosystem with the building blocks of complexity. It's a delivery system of unparalleled scale and efficiency, ensuring that the fruits of one generation of stars become the seeds for the next across vast, unimaginable distances. This process could explain the surprising chemical uniformity we observe across many large galaxies, a uniformity that was difficult to reconcile with slower, more localized enrichment processes. The black hole in its violent exhalations may be the great equalizer, the force that stirs the cosmic pot, ensuring no corner of its domain is left untouched by the elements of life. Let us also pause and reflect on the nature of discovery itself. This entire story did not begin with a grand theory or a bold prediction. It began with a subtle anomaly, a scientific loose thread, a quiet whisper in the data that just didn't feel right. It started with a handful of astronomers looking at an image and asking a simple, courageous question: why are those stars over there? It is a testament to the scientific spirit, to the dogged pursuit of outliers, and to the humility required to question a paradigm that has served us well for decades. Science does not advance in a steady linear march towards truth. It stumbles and leaps, it follows dead ends, and it is occasionally ambushed by a revelation so profound it forces a complete reorientation. This is one of those moments. The universe, it seems, takes a particular delight in hiding its most elegant secrets in the most violent and unlikely of places. It challenges us to look into the heart of the inferno and see a nursery. It demands that we discard our simple narratives of good and evil, of creation and destruction, and embrace the complex interwoven reality, where the two are not opposites, but are instead two faces of the same cosmic coin. Our journey to this understanding is a reminder that the cosmos is not obligated to conform to our expectations or our sense of order. Its truths are wilder, more paradoxical, and infinitely more beautiful than our limited imaginations can often conjure. The greatest discoveries are not those that confirm what we know, but those that gracefully demolish our certainty, leaving us in a state of renewed wonder, with a new, bigger map to explore. And so, the exploration begins anew. This discovery is not an endpoint. It is the firing of a starting pistol for a new race of cosmic discovery. A new hunt is on. Astronomers around the world are now frantically combing through archival data, re-examining old observations of galactic jets through this new revolutionary lens. Are there other examples hiding in plain sight? Have we been staring at these stellar nurseries for years, dismissing them as background noise or unrelated star clusters? The search will be systematic and painstaking, a cosmic forensic investigation on a galactic scale. But the true frontier lies with the next generation of observatories, instruments of breathtaking power that are poised to bring this phenomenon into sharp focus. The James Webb Space Telescope, with its unparalleled infrared vision, will peer through the shrouds of gas and dust that surround these turbulent regions, seeking the telltale heat signatures of protostars, the embryonic suns still swaddled in their natal clouds. Webb can perform a stellar census determining the age, mass and composition of these jet-induced stars with astonishing precision. It can answer the crucial question, are these stars normal, or are they somehow different, forged in a crucible that leaves a unique imprint on their character? Are they more massive? Do they live shorter, more brilliant lives? Simultaneously on the ground, the Atacama Large Millimeter Submillimeter Array ALMA will map the cold dense gas with exquisite detail. ALMA can see the raw fuel for star formation before it ignites. It will trace the filaments of compressed gas along the jet's path, measuring their density, temperature and velocity. We will no longer be inferring compression, we will watch it happen. We will see the shock waves rippling through the interstellar medium in real time, identifying the exact pockets of gas that are on the verge of collapsing to form a new solar system. ALMA will provide the before picture, the blueprint of the stellar nursery just moments before the lights turn on. And then there is the future, the promise of the Square Kilometre Array, the SKA, a radio telescope of continental scale that will map the structure and magnetic fields of these jets with a resolution that is today pure science fiction. The SKA will reveal the fine-grained texture of the turbulence, the intricate dance of plasma and magnetism that governs the jet's interaction with the surrounding galaxy. It will allow us to create breathtakingly detailed three-dimensional models of this entire process, moving from a static image to a dynamic, evolving understanding. With these tools, we will graduate from finding examples to building a true catalogue, a cosmic bestiary of creative black holes. We will hunt for this process across cosmic time, looking back into the distant early universe when galaxies were young and chaotic and black hole jets were perhaps even more common and more powerful. Could this mechanism be the dominant mode of star formation in the universe's adolescence? Could it be the primary way that the first massive galaxies built up their stellar populations? By finding and studying these systems at different cosmic epochs, we can build a timeline, a history of this symbiotic relationship, and understand how it has evolved over the past 13 billion years. We will search for it in all types of galaxies, from colossal ellipticals to spiraling giants like our own Milky Way. Is the black hole at our galactic centre, Sagittarius A, currently dormant, capable of such creative outbursts? Could a flicker from our own galaxy's core one day trigger a wave of stellar birth in the Milky Way's halo? The questions are now cascading, each one opening up a dozen more, propelling a new generation of scientists and explorers forward. We began this journey with a single, inexplicable point of light. We end it with a completely new vision of the cosmos, a vision where the most destructive forces we have ever discovered are also essential architects of galactic structure. A vision where the universe is not a quiet, empty stage upon which events unfold, but a dynamic living entity, where every part is connected, from the singularity at the heart of space-time to the lonely star twinkling in the outer darkness. The black hole is no longer just a gravitational anomaly. It is a part of the grand narrative of cosmic life. It is the engine that regulates, that seeds, that sculpts, that participates in the unending cycle of stellar birth, death, and rebirth. When you look up at the night sky now, at the serene beauty of the stars, remember the violence and the paradox that may have given them life. Remember that in this universe, creation is not a gentle act. It is forged in fire, born from chaos and powered by the very engines we once thought were designed only for endings. We have learned that to build a galaxy you must first summon a monster, and in that monstrous, beautiful, terrible heart the universe reveals its deepest and most awe-inspiring secret, that even from the deepest, darkest abyss new light can be born.